affect the environment. Now let's talk about some cosmology stuff. We're going to be talking about Sagittarius A star. Oh yeah. Here are the X-ray transients from Sagittarius A star. You can see it's a fairly consistent X-ray source here over the past 14 years. And it's emitting X-rays in a fairly standard state right now according to the daily, these are days of the calendar here, so we're at day 245. And that's what smAshlights is going to be all about today. Today's smAshlights. We're going to be talking cosmology and basically only cosmology. We'll also be talking about whatever we want. So if something like this happens, instead of me being like, oh my God, I've got to take it out, I'm just going to take it out to dinner instead, because it's about as scary as it was to me on January 23rd. I would let you stay there, but you're kind of cramping my style. So if you'd be so kind as to, could you? Oh, thank you. See, I'm telling you, COVID is becoming very agreeable nowadays. So yeah, the whole smAshlight is basically going to be a cosmology segment today because, again, during the smAshlights we talk about whatever we want, and the news stories today are lacking. So let's talk about Sagittarius A star and its companion stars. Yes. So Sagittarius A star is the massive radio source at the core of the Milky Way galaxy. One of the largest stars in the whole galaxy is S2. Not only is it large, it's very strange. So looking at the Milky Way galaxy, you know, the galactic core is someplace in this void-like area, and it's because there's a lot of gas and dust there, which makes it look dark. If you zoom all the way in on Sagittarius A star, while it is an X-ray source, you will not see any sort of light emitted from it. I think this is S2 right here. And the reason that we're talking about this is because of the galactic wind, yes. So, S2 is an important part of the stellar system at the core of the galaxy. During its eccentric orbit, which has an eccentricity of 0.88, which is a highly eccentric orbit, I'll show you an image of it momentarily, it reaches speeds of 5,000 kilometers per second, over 10 times what the current solar wind speed is. So we're talking about protons with the solar wind speed, folks. This is a blue supergiant star, similar to Deneb, but orbiting Sagittarius A star at 11 million miles per hour. Why is that relevant? You may wonder why that's relevant. Well, it's because all stars, and there's a diagram of its orbit. It has a 16.8 year orbit, I think it is. Somewhere around there. 16.05 year orbit. So you can imagine what the tidal forces would be like there. And the thing to understand about this more than interesting system is that every one of those stars in that system has its own set of jets. So, for example, the Sun has enduring coronal holes at each of its poles. Now let's just make this up, as we don't exactly understand the magnetosphere of these. We're not looking at radio images. But this star right here, let's say that's S2. And let's say those are the stellar polar field regions. There are jets coming out of these areas. And I'm exaggerating their shape to make a point. These objects are probably quite similar to the Sun, but they're under incredible tidal forces, which is going to completely affect the input-output of these fields. And this is why the galactic wind has absolutely nothing to do with even the plane that Sagittarius A star is on. To make matters more interesting, the orbit of the Earth in the solar system and the orbit of the Sun around the Milky Way galaxy is off by like 40 degrees. And that is why the galactic wind has nothing to do with what's going on in the solar system. So again, now you see all these giant stars. This is a pretty zoomed in view here. And all of these giant stars, they all have their own enduring coronal hole fields that are blasting out beams of protons. At the very close layers, where you see these like double rings, very close up to these stars, there are electrical features happening there. There are atmospheres, we'll call them stellar spheres. And there's a massive amount of incredibly heated up gas and dust being blasted all around in different directions around here. And the galactic wind ultimately is the net effect of all of those objects. They all affect the output of Sagittarius A star, and Sagittarius A star affects the output of all of them. They're all within each other's magnetic fields to some degree. And the orientation of these poloidal fields is really what is important in terms of the proton output of these areas. In other words, if you have these three stars, where their poloidal fields are all aimed in the same direction, these fields will become like a woven together beam of doom, and it will be chased by electrons. Electrons will be pulled out of these systems and will chase those systems. And this is, I believe, how we get these pulsing systems. Now, exactly how the poloidal fields blast out these coronal holes constantly is still a matter of massive debate. But in any case, I hope that gives you some insight into what's going on in terms of the galactic wind. And by the way, the Milky Way galaxy is too complicated for the puny solar system and Earth to be directly affected by this. The energy from systems like this gets propagated through the giant poloidal fields, which are at a huge angle, by the way. You would think that because we've got Fermi bubbles like this, and you've got a bunch of different jets coming out like this, you would think this would be somewhat perpendicular to the galactic plane, and it is not at all. Sagittarius A star is off at a crazy angle. I think you can actually see some of the jets in this image. But it's off at a major angle, first of all. So, perpendicular to that would be like this. Assuming that's the angle. It's hard to tell what orientation you're at here. And this is from a ground-based telescope. So, in any case, that's a little bit of what's going on. And by the way, the orientation of those poloidal fields doesn't necessarily have anything to do with their orbits. As we see, for instance, in the solar system, we see planets with their poles practically parallel to their orbital planes. So in any case, by the way, one of the tracks you just heard was Dr. Steelshank. It's an homage to Sam Afif. Go follow him on Facebook and tell him to stop being so cornea. He used to be the bacteria from Syria, and now he's just cornea from California. And that track is called Professor Krookenstein, and it's available at soundclick.com/goldencatproductions, our record label. And thanks to the gentleman who emailed me. By the way, we've also got a SoundCloud account. I believe that is in the links below the video as well. SoundCloud.com/Daniel-Nigro-2. How catchy. I didn't come up with that. That was SoundCloud. Now, we are streaming live to Twitch. We love the platform. Twitch.tv/smAshomash. Thanks to our new subscriber or follower or whatever it's called over there. Cheers. If you haven't checked out our Cosmology playlists, check those out. There's all kinds of different stuff on there, from talk to coronal mass ejections to composites with a whole bunch of helioviewers of the sun over a long period of time, such as 32 hours of the sun and stuff like that. Also, the video about the neutron star comet. There is a neutron star that's traveling at 141 kilometers a second across the Milky Way galaxy. Thanks to our YouTube subscribers. If you haven't pressed like and subscribe and press the notification bell to receive all notifications and hopefully, possibly even see when a video goes up, well, please do it now. No, that's okay. We'll wait. And oh, you're back. All right. Well, we welcome you. Oh my God, what has happened here? Son of my beehive. Have you pressed like and subscribe on YouTube? All right, thanks. And here ends today's